Hi, I'm John Ackerman, N8UR, and I'm happy to be here today to talk to you about what goes on behind the tuning knob of your rig, how we control frequency today, how we did in the past, and how the technology got us from there to here. If you have an HF rig, the chances are good that it looks at least something like this, and in particular that it has a digital frequency display. This one is showing a frequency in the 20-meter band, and it has a resolution of 10 hertz. Your rig might have 100 hertz, or it might even have 1 hertz. If you stop to think about it, 10 hertz out of 14 megahertz is 10 out of 14 million. That's a pretty remarkable amount of precision. And you're probably pretty confident that what the dial is showing is the frequency that you're actually on. Did you ever think about why you can be that confident? It wasn't always that way. And maybe at the end of this presentation, you'll realize that it may not be that way even now. If we go back to the very beginning of radio, the earliest transmitters and receivers were almost untuned. Transmitters were spark gaps that had very broad signals and limited range. The bandwidth of that transmitter could be 50 kilohertz, and that's operating at 500 kilohertz, so only a few stations could actually even fit into the spectrum. And to make things worse, receivers had almost no selectivity at all. So even if the transmitters were on different frequencies, the receivers couldn't tell them apart. As more stations came on the air due to commercial operators and ship to shore, and of course hams, and there was no regulation at all, there was more and more interference. And who got blamed for the interference? Of course, it was the hams. So when regulation ultimately came along, hams were banished to what was then thought the useless short waves at wavelengths less than about 200 meters, which is above 1500 kilohertz near the top of today's AM broadcast band. Well, that turned out to be not so bad because those useless short waves weren't all that useless after all. But that's a story for another day. By 1920, Spark was dying because it just caused too much interference, and it was replaced by transmitters with vacuum tubes that generated continuous wave or CW signals. These had much narrower bandwidth, also much better range, and they reduced the interference. Early tube transmitters typically just had one stage, one tube, which was an oscillator connected directly to the antenna. It was typically tuned with a simple LC circuit, and we'll talk about that in a minute. And once it was tuned up, you left it alone. There was no such thing as a VFO, and there was no ability to go up 5 or down 10, well, at least not on purpose. Uh, and the typical ham receiver was a 1 or 2 tube regenerative receiver. Now, this was a piece of really clever technology for the time, but to make it work took a little bit of magic, and you had to get the adjustments just right. And if you did, you got really good sensitivity, good selectivity, and it could tune in CW signals. But if you got it wrong, it was deaf as a post. And if on the other extreme, it would go into self oscillation and become a transmitter, which wasn't a good idea. Now, the very bravest and wealthiest hams were just starting to play with a super heterodyne receiver. That was a much better way to go for reception, and it was a keeper. Today, most of our radios are still super heterodyne designs. Between the transmitters and the receivers, narrower signals meant the frequency accuracy became more important. You had to know where to look for someone, and stability became important because once you found them, both the receiver and the transmitter needed to stay put so that you could hear it and work each other. In the 20s, the Morse code prosign QRG, what is my frequency, became very popular. There was no such thing as a frequency counter, and frequency wasn't that useful a concept anyway. Tuning was so coarse that wavelength was more practical. And remember, a long wavelength is low frequencies, short wavelength is higher frequencies. With receivers, you could use stations at known frequencies to provide reference points, but what about your transmitter? Well, the ham's friend was a wave meter, and well-equipped stations had one. It was a simple device, typically with a plug-in coil for each band, a variable capacitor with a calibrated dial, and a flashlight bulb or a meter as an indicator. You calibrated it using a receiver with known frequency stations, and then you could set it next to your transmitter, key down, and tune the capacitor for an indication on the meter or the bulb. With great care, you might get accuracy to maybe a tenth of a percent, and we'll talk about that more later. So now I need to warn you, there's going to be some tech talk. I'll try to keep it as short as I can. There's almost no math, and we'll get back to the fun stuff as quickly as we can. I already mentioned simple LC or tuned circuits in early transmitters. A tuned circuit is really the core technology of radio. Uh, it's a circuit that typically includes a coil or an inductor and a capacitor. It turns out that inductors have the characteristic of passing low frequencies but blocking high ones, and capacitors are the opposite. They block low frequencies and pass high ones. Where those two curves cross over, as shown on the chart here, is the resonant frequency. That's where the most signal gets through the circuit. This is often called an LC circuit because L is the abbreviation for inductance and C for capacitance. Tuned circuits give us selectivity and make oscillators work. They really are at the core of all radios. A characteristic of a tuned circuit is its Q. The Q is a number that tells us how sharp a circuit is. Higher Q means less loss and narrower bandwidth. So that's a good thing. If you look at the chart on the right here, you'll see a high Q circuit lets more signal through at its peak, and its peak is narrower. So it can reject unwanted signals better than the lower Q circuit. So that's always a good thing, except that it also means the tuning becomes more critical because a small shift in frequency can move you off of the peak of the signal and way down the side. So you need to be careful in how you tune a high Q circuit. And just as a fun fact, turns out Q is not short for quality. It was just the only letter left for a new electronic unit when they decided to use this. Now, tuned circuits and oscillators are used for frequency control. Adjusting the values of the inductance or the capacitance lets you tune the circuit and change the resonant frequency. The values of inductance and capacitance are determined by the physical dimensions of the components, the number of turns on the coil, the diameter of the coil, the size of the plates, and the spacing between them in a capacitor. The implications of that are that the degree of electrical tuning depends on how finely you can make a mechanical adjustment. It also means that because these are physical components, temperature has an effect on them. They expand and contract with temperature, and that will change their value, and that changes their frequency. And again, higher Q makes the tuning touchier, so temperature changes are a bigger deal. Radios drift when they first turn on as the temperature changes inside them until it stabilizes. Another kind of resonant circuit is a crystal. It turns out that crystal materials have the interesting property that if you put a metal plate on either side of a piece of crystal and put an electrical charge across it, it will torque or twist. And if you put an AC charge, you can make the crystal actually vibrate, and it acts like a resonant circuit. The frequency depends on the dimension of the crystal and the type of cut. It turns out that quartz is kind of the ideal material for this, and it's almost universally what we use. So a quartz crystal acts like a very high Q tuned circuit. So that's good. It's very sharp, very efficient, and can be adjusted very precisely. However, another really good factor is that despite it being high Q and despite what I just said a minute ago, it's much more stable in frequency than an LC circuit. There's less drift from external forces, although still some. And that's because the quartz material is less impacted by temperature changes than other materials. Also, the quartz is smaller, it's mechanically solid, and for various reasons, it is dramatically more stable in maintaining its frequency than an LC circuit. So it becomes the ideal thing to use as a resonator, particularly in oscillators. The first quartz crystal oscillator was described in 1921, and the first QST article about it was in July 1924. And you can tell that the author and the ARRL thought that this was a really big deal. Here's a quote from that article. Can you imagine a transmitter that never shifts its wavelength even a hundredth of a meter? Can you imagine making a schedule for 96.38 meters and knowing that you will be right on that wavelength and knowing that the other station will be tuned right to you? And can you imagine getting from the receiving operator a report that during the hours of operation, the beat note in the earphones never changed even a particle? These things are possible with the oscillating crystal. They were excited about this, and there was a good reason to be excited because this was a giant leap for crystal for frequency control. Now, there was a little of a downside. You can only get one frequency out of a crystal. It's not frequency agile, and it's difficult, if not impossible, to make them yourself. They're somewhat expensive, so most hams had only one or maybe a few crystals, and that meant that they could only transmit uh, on those specific frequencies. And crystals weren't really practical in receivers because a receiver needed to be able to tune. Now, uh, I've mentioned already that we could read a wave meter to perhaps 1/10 of a percent if we were lucky. And throughout this presentation, I'm going to talk several times about percentages or parts per million and sometimes even parts per billion. And it's important to get your head around that because it has some real implications for the performance of our radios. So, uh, percentage and ppm and ppb are ratios. 0.1% means 1 kilohertz at 1 megahertz or 100 kilohertz at 100 megahertz. 1 part per million is a hertz at a megahertz or a kilohertz at a gigahertz. 1 part per billion is a hertz at a gigahertz or a kilohertz at a terahertz. So the higher the frequency, the larger the span that that number could represent. But here's the rub. The tuning requirements don't scale with frequency. For example, it's usually considered that single sideband requires tuning within about 100 hertz to make the voice sound natural. Well, that's the same whether you're operating at 1 megahertz or at 10 gigahertz. So at higher frequency, there are tougher accuracy and stability requirements to meet. And it's important to keep that in mind as we talk about what kind of accuracy and stability we need. And by the way, accuracy and stability are two different terms for very important characteristics. And it's important to know which one is used when. Accuracy is how close you are to the desired frequency. And stability is how closely the oscillator stays there, how much it wobbles around. Accuracy is important, for example, to know that you're within the band. Or if your friend wants to have a sched with you to tune your radio to the frequency that he says he'll be on. Stability is important if you want to be able to keep understanding his SSB during the contact without it becoming Donald Duck. This graph is a little bit crude, but I like the way it shows the possibilities. You can have a signal that's stable but not accurate. It's not where it should be, but it stays put. You can have a signal that's neither stable nor accurate. Well, that's the worst case. You can have a signal that's accurate. On average, it's where it should be, but over the short term, it wanders around. And finally, you can have the desired signal that's stable and accurate. It's important to keep in mind whenever we're talking about percentages or ppm, whether that's accuracy or stability, because they are different things. So now the tech talk is over and we will return to the 1920s. Actually, we'll return to 1919 because that's when WWV went on the air. If you've ever operated HF, you've almost certainly heard WWV. It's the US standard time and frequency station. When it first went on the air, it was actually a time standard only. But by 1923, it was transmitting a standard frequency with an accuracy of better than 0.3%. Going back to what we just talked about, that's about 3 kilohertz at 1 megahertz or 21 kilohertz at 40 meters. By 1929, though, use of crystal control improved WWV's accuracy to better than about 1 part per 10 million. That's a hertz at 10 megahertz. That is an absolutely astounding improvement in only 6 years, but it's what crystals could do. However, it's fair to say that was not the kind of crystal that a ham would ever have. This was a very expensive crystal. If you look at the picture on the right, the crystal is inside that coil of heating wire, which is under the glass jar, which allows the thing to be pumped out to a vacuum. This was very expensive and beyond the reach of hams, but it shows what the technology would allow if money were no object. Now, your ham rig by the 30s uh, was going to be typically multi-stage, something called a master oscillator power amplifier design, which had an advantage for frequency control because the oscillator was no longer directly tied to the antenna. It didn't have to make as much power, so it didn't heat up as much. And by being isolated from the antenna, it wasn't impacted by the antenna wires swaying in the wind, for example. At the beginning of the 30s, we were still typically using LC circuits, but by the mid 30s, every well-equipped ham station had a crystal control transmitter. And if you didn't, the ARRL was looking down its nose at you a little bit. And we've already mentioned, hams typically had one or two crystals per band. You transmitted on your frequency and your friend transmitted on his, and you each tuned your receiver to find the other, which is why frequency accuracy was important. And you also had to hope that the frequency marked on the rock was correct, because it might not be. By 1941, when World War II shut things down, transmitter VFOs were just starting to appear in very expensive rigs. These were still not nearly as stable as a crystal, but sometimes that trade-off of stability and readout accuracy was worth it in order to get the flexibility. But World War II stopped further ham improvements in that for quite a while. Now, your receiver in the 30s was almost always a super heterodyne. It might have been ham band only, where you plugged in different coils for different bands and had a big knob with a dial for tuning just across that band. Or like the receiver shown here, it might have been a general coverage receiver that covered the whole HF spectrum and perhaps four different bands that were marked on the large dial. But it had a separate band spread knob. You could tune the main dial to, say, 7.0 megahertz for the 40-meter band, and then use the band spread to have fine tuning across the ham band. And this allowed you to separate signals and have much better control over what frequency you were tuned to. It didn't necessarily improve accuracy, but it did greatly improve usability. These radios were using only LC circuits for tuning because, again, you wanted to have flexibility in how you tuned the radio, and crystals couldn't do that. You had to calibrate them, usually by tuning in someone on a known frequency, and they did drift as they warmed up. You had to chase a signal up and down the band if either the receiver or the transmitter were first warming up, and it might have taken a half hour or an hour to fully stabilize. In 1931, before crystals were ubiquitous, the ARRL was getting concerned about the number of hams that were operating outside the band, and these folks were getting love letters from the FCC telling them that they were outside the band. So the league held its first frequency measuring test. Three well-known ham stations transmitted on 80 and 40 meters. FCC monitoring stations measured the frequency and reported it to the ARRL. And hams participated. You'd measure the frequency and send your results in, and the league would compare your results with the FCC's. And if you were within 0.1%, you would win a certificate. And that meant 3.5 kilohertz on 80 meters or 7 kilohertz on 40 meters. There were 212 participants, and the league was actually pretty discouraged about this. So many people were operating outside the band, and sometimes as much as 100 kilohertz outside the band. They hoped that more folks would take it seriously, but that was what they got. Of the 212, 144, or just about two-thirds, were able to accomplish that and get the certificate. The winner was W2BP with a 99.999% average over, I think, 15 separate readings. That's within 35 to 70 hertz. And that's really impressive for 1931. There are ham rigs today that could not meet that requirement. From the 30s through the 70s, not a whole lot really changed in frequency control for ham radios. There were some improvements after World War II. VFOs got better, and they became common in high-end transmitters to allow for frequency agility. Still not as good as a crystal, and in fact, novices were not allowed to use VFOs, but novices had to use crystals because the FCC was afraid that inexperienced operators would screw things up and be out of band. Collins Radio introduced the permeability tuned oscillator, or PTO, that really set a new standard. On the receiver side, double conversion receivers started to show up. This is a type of super het that had a crystal controlled first oscillator that would mix the input frequency down to a lower frequency. So maybe 10 meters at 28 megahertz might be mixed down to 1 megahertz. And then a variable oscillator would provide a second injection frequency that would tune the signal from that lower frequency, and then it was demodulated. That lower frequency variable tuning was more stable and accurate than trying to tune up at 10 meters. So these provided much better performance at higher frequencies than the older radios. Another post-war innovation was the crystal calibrator. And this is really simple, but it might have been the biggest improvement of all. A crystal calibrator was simply a 100 kilohertz crystal in your receiver in a circuit that would generate lots and lots of harmonics when it was turned on. You'd turn the calibrator on, and then first of all, tune in, say, WWV, and adjust the crystal frequency to 0 beat, the WWV carrier. Then after that, you could tune to any 100 kilohertz point in the receiver's span and adjust the dial to match the calibrator location. And that would allow you to get very accurate calibration, at least for the frequency above and below where you calibrated. And that was just a huge improvement from something very, very simple. Now, in physics, things really changed between the 30s and the 70s. World War II was the main driver of that. Quartz crystals got much better. The oscillators were better because we had ovens and voltage regulators that were better. They learned about new ways to cut the crystal to get better performance. But there were other huge advantages, particularly in atomic physics as part of the atom bomb project, and microwave radio as part of the radar developments, that led to the recognition that quantum effects inside an atom could be used as a way to generate or find an extremely accurate frequency. If you did all the math, you could precisely calculate what the frequency should be when an electron in an atom jumped from one quantum state to another. And if you exposed that atom or many of those atoms to a strong RF frequency at the right frequency, you could find the point where that resonance occurred. And that was extremely accurate. It was very much not impacted by temperature or other effects, and offered the possibility of an atomic clock that was tremendously better than a crystal oscillator could ever be. The first atomic clock was built in 1949 at the US National Bureau of Standards, and it used ammonia. It was actually less accurate than a crystal, but it showed that the idea worked. By the mid-50s, it was realized that the metal cesium was ideal for this purpose. And the first cesium atomic clocks were developed at NBS and also at National Physical Laboratory in the UK. And these were really, really good. They were agreed with each other very closely. And the cesium transition actually became the way that the unit of frequency, the hertz, and the unit of time, the second, are defined. A cesium atomic clock is by definition on frequency. It may have noise that limits how precisely you can measure its frequency, but the frequency it's oscillating at is by definition correct. And that frequency could now be accurate to less than 1 part per trillion. So that's a hertz at a terahertz, which is fairly good. But amazingly enough, now that we're in the 21st century, new quantum transitions at optical frequencies rather than RF frequencies promise orders of magnitude better than that. And I think within 10 to 20 years, we're likely to see the hertz and the second redefined to a new transition from one of these optical clocks, and will be much more accurate even than we are today. Now, getting back to ham radio again, in the mid 70s, fancy HF rigs started to have digital frequency displays, which are really frequency counters with a crystal reference that counted the number of cycles of the VFO and of the other oscillators in the radio and mixed them together and displayed the tuned frequency. Now, this gave us better precision and perhaps better accuracy, but did not improve the stability. We still had a VFO that might drift. So the digital display was neat, but it wasn't a game changer. In my mind, though, the real advance in the mid 70s was the frequency synthesizer. Synthesizers are a way to generate multiple frequencies from one or a handful of crystals. They were used in science and industry from probably the late 50s, but were extraordinarily expensive and complicated. Digital technology let us make much simpler ones. The first ham use was in FM transceivers. As more and more repeaters came along, uh, it became very expensive to buy a pair of crystals for each repeater in your neighborhood. So someone realized that they could come up with a circuit that would generate multiple frequencies and that could replace the crystals. A couple of companies did that. The one shown in the picture here is the GLB channelizer, which would let you dial in any frequency in the 2 meter band with 5 kilohertz resolution and replace all those crystals. It was a pain to wire it into your radio, but it worked. And ultimately, ham manufacturers built synthesizers into their FM rigs. And by the late 70s and into the 80s, it was very common to have synthesized FM rigs. We didn't really see it in HF rigs though at that time. Now, how do these synthesizers work? Well, I mentioned some early ones that were used in science and industry, and they were huge, and they work by multiplying and mixing several crystals together to generate new frequencies, but they weren't really practical for ham use. Uh, Digital technology allowed us to use something called a phase lock loop, or PLL, because digital dividers were available. The drawing here shows how a PLL works. Over on the right-hand side, there's something called a VCO. That's a voltage-controlled oscillator. So its frequency will change based on a control voltage that you feed into it. And let's pretend that this one is tuned to 100 megahertz, more or less. And it's generating that roughly 100 megahertz signal. Part of the output is taken and it's fed into a digital counter that divides the 100 megahertz down to 1 megahertz. And then there is a crystal oscillator in the system that's also running at 1 megahertz. And the output of the crystal oscillator and the counter are fed into something called a phase detector. If the two frequencies are identical, the phase detector outputs a 0 voltage. But if one frequency is higher or lower than the other, the voltage goes up or down. And that voltage is fed back into the VCO to adjust its frequency. And ultimately, everything stabilizes with the VCO frequency following the crystal reference frequency. So now we can have our 100 megahertz frequency that's locked to the 1 megahertz crystal reference. Now, by itself, that doesn't let us have many frequencies, but as technology advanced, the counters became extremely sophisticated. And today, we can have a synthesizer like this that allows us to generate nearly unlimited frequencies, sometimes over a range of hundreds of megahertz from a single reference crystal. And that's the technology that has made our modern radios work. And in fact, virtually all radios today use PLL synthesizers. HF rigs have a typical resolution of 10 hertz or sometimes even 1 hertz. The typical stability, which is coming from that crystal, not from a VFO anymore, is from 20 parts per million, which is about 200 hertz at 10 megahertz, down to 1 part per million if there's a temperature compensated crystal oscillator in a more expensive radio, or zero point 0.1 ppm or even better if the radio uses an oven controlled crystal oscillator that keeps the temperature extremely stable. Some higher end rigs have external frequency reference inputs as well, so you can lock the radio to a high quality external oscillator. If you happen to have an atomic clock lying around, you can use that as an input and really know that you're on frequency. Be careful though, not all are what you'd think when you look at these external references, inputs. Some of the ICOM rigs use that input like a frequency calibrator. You put a signal in and then push a button in the radio and the radio calibrates itself against the frequency, but it's not locked to it. The radio continues to free run. So the frequency might not be where you think it is an hour later. Some of the newest rigs have software calibration where you can tune in WWV and push the button and the rig will align itself against WWV frequency, which is really cool. Software-defined radios, which are the latest radio technology, do most of their tuning in software and may not have a traditional PLL, but the same kind of concepts apply. Now, it's important here to mention that 20 part per million down to 0.1 part per million, That's talking about stability and not accuracy. Your radio, when it comes from the manufacturer, is probably fairly close to where it should be, but you need to calibrate it so that you know that the reference crystal is on frequency. And that's what these external inputs or uh, WWV kind of calibrations help you do. So you can't assume just from that specification of how many parts per million that the radio is that accurate. That's how much the radio will drift or bounce around, and accuracy needs to be determined by looking at a known reference frequency in some way or other. So why does all this accuracy and stability stuff matter? Well, signals with narrow bandwidth allow more stations to share the band, and that reduces interference. They have better signal to noise ratio because the power is spread across less space. If I have a 100-watt transmitter and it's generating power in a 10 kilohertz spectrum, that's a lower density than if that same 100 watts is spread across only 100 hertz. So the narrower signal has better power versus the noise that's out there in the universe. And similarly, the receivers can be more sensitive. If they have less bandwidth, that's less noise getting in to compete with the signal that you're looking for. So narrow signals are good, but narrow signals bring along with it the requirement for better tuning. As we operate at higher frequencies, this becomes even more important. And I've already talked about single sideband being, within about 100 hertz. Well, at 80 meters, that only requires 30 parts per million, which any modern rig can maintain. But if you want to operate at 1296, 100 hertz is more like 80 parts per billion. And that's a different matter and much harder to have. So high frequency increases the stringency of the oscillator requirements. And another area is the type of signal you're using, the mode. Modern weak signal digital modes, particularly those in WSJT, care about drift and accuracy as well. FT8 requires less than 3 hertz of drift over a 15-second transmission. And that's probably not too hard to achieve, at least at HF or low VHF frequencies. The whisper mode requires less than 3 hertz over 2 minutes. And that could be a little bit tougher. The MSK 144 mode that's used for meteor scatter at VHF doesn't care much about drift because its transmissions are very, very short, but it does care about accuracy. The receiver and the transmitter need to be within about 200 hertz of each other to get decodes. So there's a case where accuracy is important rather than drift. So, if you are now convinced that you need to have a better reference in your radio, you might consider asking your significant other to get you a GPS DO as a present. A GPS DO is a GPS disciplined oscillator. The GPS navigation system relies on atomic clocks for timing, and inexpensive GPS receivers can output a very precise pulse per second signal. That signal can be used as a reference to see our crystal oscillator, which creates a GPS disciplined oscillator. It's really another example of a PLL. We take the crystal oscillator output, divide it down to 1 pulse per second, and then compare that pulse per second with the one from the GPS and steer the crystal until they track each other. And that gives us the short-term stability of a crystal with the long-term accuracy of the GPS. With a GPS DO plugged into its external reference, your rig can be accurate to a few parts per trillion. A GPS DO is also useful for a reference for a frequency counter or a signal generator if you have a bit of a test equipment set up in your basement. And they're not necessarily super expensive. You can get them from many sources, particularly on eBay, where you find surplus telecom units and lots of new units coming from China, typically less than $200 for most of those. And they're all usable and pretty good. Commercial name brand units can be several $1,000s, but there's at least one unit oriented toward experimenters and hams from the UK that's about $150, and it works really, really well. So GPS DO doesn't need to be expensive, and if you're into precise frequency measurement, it's definitely the best piece of equipment you can have. So let's go back now to 1931 to wrap things up. Remember that the frequency measuring test in 1931 had, I think, 212 participants, and the league was not real thrilled with that. Well, they didn't give up. They kept doing FMTs until the 80s, when the advances we've talked about, digital readouts and synthesizers, dropped the interest, and folks weren't participating, so the league stopped the FMTs. But in 2007, they decided to try again, and surprisingly, there were a lot of people interested simply for the sake of seeing how well they could do. And there's now a dedicated group of FMT nuts who do several measurement runs a year. Almost all of them use GPSDOs, by the way, and the winners are often less than a hundredth of a hertz off. And what's really interesting is their biggest challenge isn't the hardware. They can receive and measure the frequency much more accurately even than that, but it's what the ionosphere does to the signal. When the transmitted signal bounces off the energized layer up in the high atmosphere, it's shifted by Doppler effect as the layer goes up and down, as clouds of ions move back and forth. There's various kinds of smearing and fading, and that does horrible things to the signal. So by the time you're receiving it and trying to measure the frequency, rather than a sharp line, it's a smeared out mess. And these folks who are the FMT nuts are learning how to read that data and interpret what's going on. And they're actually participating in space science, because this is helping us understand how the ionosphere works. And the HAMSI organization is actually using this kind of frequency measurement with WWV as the source to do amateur space science. So that's very cool. So we've talked a little bit about how we measure frequency today and how we generate it and how we used to and what's changed. And now I'm very happy for the time remaining to take any questions. Thank you very much.